All right, everybody, welcome back. Let's do some review for the upcoming first exam. All right. Part of the trick here is understanding, what rules to look out for and things like that. So hopefully that can help you find what to look for. All right. So in the first problem, y is x times the sine of x. They want us to find dy dx, basically find the first derivative, okay? So think about what rule you're going to need to use here. We've got x times another function of x, so we're looking at the product rule here, okay? So the derivative of the first x is 1 times the sine of x plus, I'll keep the first x times the derivative of sine, which is cosine. So it looks like we're getting sine of x plus x times the cosine of x back. And that's choice B, okay? So hopefully not too bad there. Again, you're multiplying functions of x, looking at the product rule. Okay, number 2, if f of x is 7x minus 3 plus the natural log of x, then find f prime of 1. Okay, so we're looking for the instantaneous rate of change of this function at 1. In other words, we're looking for the slope of this function at 1. So let's take the derivative, and then we can plug 1 in. So the derivative of 7x would just be 7. The derivative of the 3 is 0 because it's a constant, but watch this function. The derivative of ln of x, 1 over x. So there's our first derivative, and now we can evaluate at 1. And it looks like we get back 8. Okay, so the slope of that function at 1 is 8. Okay, moving on to number 3, we have a graphical function here, and we're looking at some limits. The graph of the function f is shown above. Which of the following statements is false? Okay, so we've got to find the one that's not true. A, the limit as x approaches 2 of this function exists. Is that true or false? Well, as x gets close to 2 from both sides, the y value also gets close to 2. So that limit exists. That's true. All right. The limit as x approaches 3 exists. Well, again, as I come into 3 from left and right, I do approach the same y value of 5. That is true as well. Number 4, the limit is x, part C, excuse me, the limit as x approaches 4 of this function exists. Well, from the left, we approach a y value of 2. From the right coming into 4, we approach a y value of 4. Okay, so the left and right-handed limits are not equal here. So this limit does not exist. We found the one that's false. Okay, let's make sure the others are true, though, quickly, just in case we made a mistake. Always good to go through all of them. As x approaches 5, yes, we approach, it looks like the y value of 6 from both sides. That's fine. And the function f is continuous at 3. Sure it is. We've got kind of like a high point there, but there's no hole, there's no open circle there. That is continuous at 3. So that is also true. All right, so I'm confident that C is the one that's false. Okay, number 4, y is quantity. X cubed minus cosine of x raised to the 5th power. Find y prime. Okay, they could have also said find dy dx. Same thing. Here we have a quantity raised to a power, so what are we looking at? Chain rule. The outermost thing is that power of 5. I'll bring that down. I'll leave everything inside the quantity alone for the time being, and I will subtract 1 from my original power. Now I will multiply this by the derivative of the inner quantity. Derivative of x cubed, 3x squared. The derivative of negative cosine will be positive sine x. Okay, and now we're basically looking for this. Sometimes on multiple choice they'll distribute. I don't think they did that here. Let's see, we've got a 5. This is not quite right. That's the wrong quantity inside there, so we don't want that. Looks like it's going to be choice E. There's that quantity of the 4th times that chain portion. Oh, there it is, choice E. All right, moving on. Number 5, we have a piecewise function. F is quantity 2x plus 1 times x minus 2, all divided by x minus 2 for all x values not equal to 2. At x equals 2, the y value is some number k. Let f be the function defined above. For what value of k is the function continuous at 2? Okay, well, for the function to be continuous, it needs to be defined at 2. It is. It equals some number k, which we got to figure out what that is. Also, to be continuous is to mean that the limit as x approaches 2 exists. So if we want to look at the limit as x approaches 2, we're actually going to use this top piece. As x approaches 2, we never actually get there. So we're going to use this top piece. to evaluate the limit. Okay, now what you should notice is that you're going to get 0 over 0 in this thing. Okay, and what would we do? We would factor and cancel. Well, it's already factored, so we got to think to simplify this. Now if I plug 2 in for x, the limit approaches 5. Okay, so the limit's going to approach 5, and what do we know? We know that the limit as x approaches 2 of this function will need to equal f of 2 in order to be continuous, right? These two values must be the same. So if the limit's going to approach 5, then f of 2 itself must equal 5, so k itself must equal 5 as well. And there we have it. Okay, number 6. If f of x is the square root of x squared minus 4 and g of x is 3x minus 2, then the derivative of f of g of x at x equals 3 is, okay. You know, there's different ways we can do this. I could do this. I could say, look, let h of x be f of g of x. And then essentially what we're looking for is we're looking for h prime of 3 here. Okay. So, you know, this can get a little tricky because you have to realize, look, we got a function within another function, and we're going to have to use the chain rule here. To take the derivative, just like in the lesson, I would take the derivative of the outer function, that would be f prime, leaving the inside alone, times the derivative of the inner function, g prime of x. So we can do it this way. But what this means, though, now is I got to figure out what is f prime of g of x and what is g of x. Okay, g of x isn't too bad here, right? G of x is 3x minus 2, so g prime of x is just going to be 3. All right, so we kind of highlight this. That's that guy. But I also need f prime of g of x, and that can seem a little strange. Let's take a look at f. So again, f is this quantity, so I'm going to write it as the 1/2 power. And now, using the chain rule just on this, I'll bring down the half, leave the inside alone, subtract 1, times the derivative of the inside, which is 2x. Okay, so those cancel, and I'm basically left with x in the numerator and then the square root of this quantity in the denominator because of the negative 1/2 power. That's what f prime of x looks like. But I don't want f prime of x, I want f prime of g of x. So what's that going to look like? Well, let's sub g of x in. F prime of g of x is going to be, so anywhere I see the letter x, I replace it with g of x. So I'm going to have g of x squared in the numerator over the square root of g of x squared minus 4. That's what f prime of g of x looks like here. Okay, but now I've got all this stuff. Okay, so look, let's put it all back together up here. H prime is going to be g of x squared over square root of g of x squared minus 4, that's this, times g prime of x, which is just 3. And now I can evaluate this at x equals 2. So let's see, h prime of 2 is going to be g of 2 squared over the square root of g of 2 squared minus 4 times 3. And we got to figure out what g of 2 is. So we come back to our g function, and g of 2 is going to be what? 6 minus 2 is 4. So it looks like g of 2 is 4 here. So we're going to get 4 squared over radical 4 squared minus 4 times 3. So we got 16 over the square root of 12 times 3. We've got 48 over radical 12. And now we got to try to find what's going to match up with that. And, you know, this is, again, kind of a big pain in the butt here. All right, let's see. Square root of 12 is going to be 2 radical 3. So here we're going to get 24 over the square root of 3. All right, not an answer choice, and it looks like maybe a mistake was made. So I see radical 21s and I see radical 5s in our answer choices. So in any event, you know, this is a tough way to go through this problem. All right, it's easy to make a mistake. I think I just evidenced that. I wouldn't go about it like this, okay? Here's a better way to do this particular problem that I think will be a little more convenient. Since we know both of these functions, what we can actually do is figure out what f of g of x is to begin with, then take the derivative of that instead of trying to go through this complicated chain rule process. with multiple functions, and it gets real tricky, okay? So look, again, I'm going to let h equal this thing, but let's actually figure out what this is. What happens if I plug g of x into the f function? Well, that becomes the square root of 3x minus 2 squared minus 4. That is what f of g of x would look like for this particular composition, okay? And now we can just take the derivative of this thing. So again, I'm going to write this as the 1/2 power. And we do have a bit of a chain here, okay? If you want to clean it up a little, like you can square this out first, not the worst idea in the world. That would become 9x squared minus 12x plus 4, and then there's that minus 4 hanging out still. Okay, double check that by foiling that out if you need to. And the 4's are going to go, and so now it looks like we have this quantity. That's our h of x, which is f of g of x. Now taking the derivative is still a chain rule, but it's not nearly as complex as what we just saw. So I'll bring that down. And the derivative inside, 18x minus 12. And if I clean this up, I'm going to have 18x minus 12 in the numerator. I'm going to have a 2 in the denominator, and then this thing under the radical in the denominator. Okay, so there's h prime of x. And now we can evaluate at 3. Let's see what we get. 18 times 3, 54, minus 12 is 42 over 2 radical. And let's see what we get in here when we plug 3 in. 81 minus 36 is 45. Okay. And let's see, this will become 21 over radical 45. And let's see what happens when we simplify. So 45 is 9 times 5, so 3 radical 5, 7 over radical 5 when we simplify. There it is, choice A. So I don't even know what the heck I did wrong the first time I attempted it. I would certainly say if you can get the composition together like we can here, do that, then go through the derivative process. But again, just a particularly tricky question here. Okay? Just going to move that stuff out of the way for the next problem, okay? All right, so number 7, we got a limit here as h approaches 0. Now, if I plug 0 in for h, I get ln of 4 minus ln of 4, which is 0, over 0. So this is indeterminate form. Okay, but here's the thing. There's no algebra we can do on this to clean this up. There's not like we're going to factor and cancel here. It's not like we're dealing with radicals, so we're going to multiply by binomial conjugates. It's nothing like that. And this is actually a non-calculator problem. Well, this isn't really a limit problem. I really call this a derivative in disguise. I'd like to remind you about something. The definition of derivative, f prime of x, is the limit as h approaches 0 of f of x plus h minus f of x all over h. And the derivative at a specific point A is the limit as h approaches 0 of f of a plus h minus f of a all over h. Well, the thing is, we have this limit as h approaches 0. We're basically subtracting the same function from itself in the numerator. And we have this letter h in the bottom. Looks an awful lot like this limit. We have a limit as h approaches 0. We more or less have the same function we're subtracting in the numerator. One of them has the plus h in it, the other doesn't. And we have that h in the denominator. This is what I call a definition of derivative problem. Or a definition of derivative limit. Okay? We are dealing with a value in the function, the number 4 plus h, instead of an x plus h. That means we're dealing with this. Okay, notice here we have a number plus h versus an x plus h. Okay, so what you got to kind of do is recognize this as looking like the definition of derivative and understand what it really tells you to do. All this represents is the derivative of this function evaluated at 4. If you replace the number 4 with the letter x, whatever's in the parenthesis with h, you replace that with an x. That's what's telling you this is your function. So here in this limit, our function is the natural log function. The fact that the number 4 is in there means we don't want f prime of x. We want f prime of 4 for this function. That's what this limit is getting at. It is exactly this. Okay? In fact, if I replace the letter A with the number 4 here, that's what we have, okay? Where our function is the natural log function, and we're evaluating it at 4. So now we know what we're doing. Okay, the function's ln of x. This limit means take the derivative and evaluate at 4. Well, the derivative is 1 over x, and to plug 4 in, we get 1 over 4 back. These types of limits you're going to encounter more and more, and it'll take some practice, but you'll get more and more used to them. But this is why we study definition of derivative. So that it's not about taking limits. It's about recognizing when we really have a limit that represents a derivative. Okay? But reach out with questions and try to get some more of those for you in the future. Okay, number 8. The function f is defined by f of x equals x over x plus 2. What points xy in the graph of f have the property that the line tangent to f at that point has a slope of 1/2? Okay. Well, think about how we're going to set this up. We want the slope to be 1/2, right? How do we find slopes of functions? We take derivatives. So here we're basically being told, find the x and y values such that f prime of x itself equals 1/2. All right, so we'll go ahead and take the derivative of this. And it looks like we're going to be using quotient rule. Derivative of the top times the bottom minus derivative of the bottom times the top over bottom quantity squared. And we're going to get back 2 over quantity x plus 2 squared for the derivative. Okay, so there's the first derivative. What we're not going to do is plug 1/2 in for x. We're rather going to set the derivative equal to 1/2, and then we can solve for x. Okay, so let's see, I'll cross multiply. I'll take the square root. Now be careful here. When I take the square root of both sides, I got to remember a plus or minus on the right. So if I subtract 2, I'm going to get two things. Positive 2 minus 2 is 0, or negative 2 minus 2 is negative 4. So it looks like we had two x values that'll make the derivative equal to 1/2. And with a little common sense, it looks like it's going to be choice C, because those are the ones with the correct x values. Not a bad idea to verify we get the right y values, though. So what do? We go back to this function. If I plug 0 in, I get 0, so that's the point 0, 0. That seems right. If I plug negative 4 in, we're getting negative 4, which is positive 2, so that's the point negative 4, 2, and that also checks out. So choice C it is. Okay, the slope is 1/2, set the derivative equal to 1/2, and then solve. Okay, number 9, if quantity x plus 2y times dy dx is equal to 2x minus y, what is the value of the second derivative, d2y at dx2, at the point 3, 0? Now, the reason this notation looks like it does, you'll notice the 2's look like they're in different places because they are. It actually makes sense. How do we find a second derivative? Well, we take the derivative of the first derivative. What does that look like notationally? To take the derivative with respect to x, we would have a d over dx. That's the command. Take the derivative of what follows with respect to x. Well, we want to take the derivative of the first derivative. That we write as dy over dx. So now look at the math. Up top, we have kind of like this d squared in that y by itself, but on the bottom, we have this entire dx squared, which is what that notation represents. It kind of means that, not just the letter x. But that's why the 2's are where they are. We're taking the derivative, okay, we're taking the derivative of the first derivative to get to the second derivative, okay? And so that's what we want to do here. Now, before we begin, I would highly recommend let's get this by itself. So I'm going to divide this quantity over. And now we've got quotient rule and implicit differentiation because we got y's mixed into this thing, okay? So check out how this works, right? So the second derivative will equal, okay, quotient rule, we're going to do the derivative of the top first. So the derivative of 2x is 2. The derivative of y, negative y, is negative 1. dy dx. That's the implicit differentiation. There's the derivative of the top times the bottom minus derivative of the bottom. The derivative of x is 1. The derivative of 2y is positive 2 dy dx times the top, all over denominator squared. And there's our second derivative, okay? And now what we want to do is we want to evaluate it 3, 0. So basically anywhere we see the letter x, we're going to plug the number 3 in for that. Anywhere we see the letter y, we're going to plug a 0 in for that. However, there's another thing to consider. Dy dx shows up twice in the second derivative. So we actually need to evaluate this at the point 3, 0 as well. Okay, so I'm going to do that off on the side. Dy dx evaluated at the point 3, 0. Okay, so it's going to be 2x minus y. 2 times 3 minus 0, and then x plus 2y equals, what's that, 6 over 3 is 2. Okay, so all dy dx's will get replaced with 2's. All regular x's will become 3's. All regular y's will become 0's. So this thing evaluated at 3, 0 becomes, okay, 2 minus dy dx was 2. Give myself a little more room. And then x plus 2y, 3 plus 2 times 0, minus 1 plus 2 times dy dx was 2. 2 times 3 minus 0, all over denominator 3 plus 2 times 0 squared. And let's see what we get. Well, this is 0, so that's 0. We've got the negative of 5 times 6 over 9. Negative 30 over 9 is negative 10/3. There it is, choice A. All right, so again, watch those. It's not uncommon with implicit differentiation to see dy dx show up in the second derivative. And that's exactly what happened here. Okay, number 10, let f be a function that is continuous on the closed interval 2, 4, such that f of 2 is 10 and f of 4 is 20, which of the following is guaranteed by the intermediate value theorem. Okay, so again, this was part of the continuity stuff. If a function is continuous on a closed interval, then it means whatever y value you're going from to whatever y value you're going to, you got to hit every y value in between. And there will be an x value within the given interval that goes with that y value. So what's going on here? Well, look, we're on the interval 2, 4. So let me kind of make this real quick. We know that f of 2 is 10, so the y value at 2 is 10. The y value at 4 is 20. We know this function is continuous. Now, we don't know what exactly it's doing. It could be doing something like that. It could be a straight line. You know, it could be doing any number of things. It could be going up, down, real high. Or we have no idea, but we do know it's continuous, okay? Since it's continuous, okay, basically the easiest thing to look at is this pink one. And this is going to be true for all of them, though, but because this is continuous, to go from this y value to that y value, eventually you're going to hit every single y value in between, okay? And so as we look at these answers, let's take a look. A says f of x equals 13 has at least one solution on the interval from 2 to 4. Will the y value ever have to be 13 at least once between the x values of 2 and 4? Well, let's see. There's 13. Yes, at some point between the x values of 2 and 4, there's going to be an x value such that the y value of 13 is there. Okay, that's got to be the answer. Now, there's no guarantee that f of 3 itself is 15. Will we hit 15 somewhere in the interval? Absolutely. There's no guarantee that's going to occur at 3. We don't know that much about the function. F attains a max on the open interval 2, 4. That has nothing to do with the intermediate value theorem. First derivative stuff, again, has nothing to do with the intermediate value theorem. If the function's continuous on a closed interval, we're going to hit every y value in between to go from 10 to 20. We got to hit 13, and there's going to be some x value to go with it. That's why the answer is choice A. Okay, number 11. This is a calculator one, but a good one, so I put it on here. The graph of y equals e to the tan x minus 2 crosses the x-axis at one point on the interval 0, 1. What is the slope of the graph at this point? okay? So basically we want the slope, we want the first derivative at some point, but we don't know what the point is yet, okay? The clue is that this function is going to hit the x-axis somewhere on this interval. So I'm actually going to get out my calculator, and I'm going to go into y equals, and I am going to graph this function. All right, so I'm going to do e to the tan x. Make sure you are in radian mode for this class, always. Okay, so e to the tan x, close that up, minus 2, and then I'm going to change my window to go from 0 to 1. And this is what I'm looking at for my graph. Not anything crazy or too exciting, it kind of looks like this. And indeed, it hits the x-axis at one spot between 0 and 1. So what I'm going to do, I have this graphed in y1. In y2, I'm going to graph the x-axis, which would just be y2 equals 0. And now the reason I do that is I can now use the intersect function. So I'm going to do second calc. And I'm going to go to number 5, intersect. And I'm going to get the cursor as close to this as I can on my screen and hit enter 3 times. Enter, enter, enter. And it's giving me the x value of about 0.606. And you'll learn that in this class, when we round to about 3 places. Or we actually always round to 3 places, which makes sense given these answer choices, okay? So in any event, this is the x value where the slope is going to... This is the x value where we cross the x-axis. This is not necessarily the answer to this problem, though, okay? So we found where this function crosses the x-axis. We got that. Now we want the slope of this function at that value. So we want the derivative. All right, so we got to take the derivative of this. So the derivative of e to the tan x, well, that's more than a plain x up there, so we're going to use chain rule. So we're going to get back e to the tan x to begin. That's the first part of the chain, right? Derivative e to the x is itself, times the derivative of tan x, which is secant squared x. The derivative of the minus 2 is 0 because it was a constant. So there's dy dx. And now I can evaluate this at x equals 0.606. And so I'm just going to punch that into the calculator now. E to the tangent of 0.606 times, so for secant squared, we're going to have to do 1 divided by cosine of 0.606 squared. Okay. Just be careful of the secant function on the calculator. You got to do 1 divided by cosine squared. Okay, when I punch the whole thing in, I am getting about 2.95999, 2.960, closest of which is that. Okay, so in rounding, we get that as the closest value. Okay, so again, kind of a tricky problem. By the way, all these are off old AP exams. Every single one of these questions from an old AP exam. And number 12, and again, omit 13, that has a limit as x approaches infinity. I didn't realize that when I made that. We'll get to that a little later. But we'll do number 12, and then I'm going to stop this video, and then I'll do another video for the second half of this packet, okay? A person whose height is 6 feet is walking away from the base of a street light along a straight path at a rate of 4 feet per second. If the height of the street light is 15 feet, what is the rate at which the person's shadow is lengthening? So I think that's what that dark line in front of the person is, right? If the light's coming from here, then this is going to be our shadow. I'm going to call that S, okay? What do we know? Person is 6 feet tall, street light is 15 feet tall. And the trickiest thing here is kind of seeing what's going on. Let's see. Person 6, we labeled that. Walking away from the base of the street light along a straight path at a rate of 4 feet per second. So look, here's the thing. The shadow is going to be lengthening this way, but this right here, this is where the person is walking. So I'm going to call this W, okay? And what we kind of have here are similar right triangles. And got to go back to geometry to remember, if you have similar triangles, right? Angle, angle. Makes similar. Clearly both big and little triangle share that angle. They're both got a 90-degree angle, so they are similar. And so with similar triangles, sides form proportions. And this is what's going to allow us to get things together now. Okay, now this 4 feet per second is the rate at which the person is walking. That is dw dt. We are looking for the rate at which the shadow is lengthening. We want ds over dt. Okay, and so what I'm going to do to set this up, look, the height is our constant. The person's 6 foot tall. That's a constant. The street lamp's 15 feet tall. That's a constant, so I can use those as I build my equation. So watch how I do this. I'm going to do bottom of the triangle over the side. Okay, so S over 6 equals bottom of the triangle. You got to be careful here. W is what I'm calling the walking distance. That's behind the person. S is in front of the person. What's this whole length going to be then? W plus S. Over its side, 15. And so what we just did was set up proportions. Bottom over side equals bottom over side. Okay? And now we can take derivatives, but I'm not going to do that. I'm actually going to cross multiply here. And I'm actually going to get s's on one side of the equation. Now I can as easily as possible take the derivative with respect to t on both sides. Derivative of 6w would be 6 dw over dt, and on the right 9 ds over dt. And there's our derivative, and let's sub in what we know. We know dw was 4, so 6 times 4 equals 9 times ds dt. 24 equals 9 ds dt. So we're looking for 24 over 9, and if we punch that in, I'm guessing we'll get back one of these values. Let's see, 2.6 repeating it is. Okay, there you go. So again, you know, related rates can be tough. There's no way to study every possible problem. I did a bunch of problems in my lessons with you. We never saw, similar right triangles for a setup. We saw Pythagorean's theorem a lot. We saw cylinders and cones and spheres and areas and things like that. But we never saw something like this, and this is part of what's tricky about calculus, is that you can't really account for every possible algebraic scenario there is to set up a problem. Okay, it's just a lot of success relies on your ability to remember your algebra and your geometry from years past. Okay, but we'll stop there for now. Take a breather, try the other half, and then you can check the next set of solutions when I get that up. Have a great day.